So this month, I think it's our 13th Kokkos Tea time, and we're extremely happy to welcome Wolfgang. I don't know how to pronounce your name, so please excuse me if I Bangerth. So I believe you're from the University of Colorado, if I'm correct.
Almost. There's two big universities in Colorado. One is the University of, and the other one is Colorado State University, and I'm from the latter. Yeah.
Okay, sorry. And so you will tell us about the use of C++ modules and this new feature that came with C++20. That is really a new way to distribute code. Does it actually work? Can we use it? And can we maybe use it with or for Kokkos at some time? So thank you very much for being here, and I leave the floor to you.
Okay. So I will apologize up front. I intended to make a presentation and then ran into the fact that I'm teaching 3 courses and just did not get to it last night. But so what I'll show you is a few code snippets of how this looks like in C++ that I pulled from a paper that I wrote, and I'm going to show that to you in a second. But perhaps to start this, so in C and by inheritance in C++, when you have a library that exports certain functions or classes, for example, you traditionally put those into a header file. And then in a place where you want to use this, then you would have a pound include the name of the header file. And the way this is described and the way this actually happens in practice is that this is a literal include. So the compiler basically just copy pastes the entire content of that .h file or that .hpp or whatever suffix you want, literally copies all of the content of that into the file where it is being included. And of course, that can happen transitively many times over. Because the header file itself might also pound include other things. And if you look at this, then this might add up to tens of thousands, and in some cases, hundreds of thousands of lines of code that end up being in this file that ultimately will be handed over to the compiler, right? So all of this happens in a phase that is called pre-processing, which happens before the compiler even ever sees any code. And so it's perhaps not a surprise that this is an expensive scheme, right? I mean, this was what people could do in 1967 when C was invented. But it leads to very, very large files. That was perhaps not what they anticipated in the 60s. But today, if you include substantial fractions of, let's say, the C++ standard library, then you do end up with very large files. And what makes this awkward is that you then ask the compiler to read through these tens of thousands or hundreds of thousands of lines of code and understand them, right? And so every time you compile a file that includes, let's say, angle bracket set, for example, the compiler has to start from scratch, reading and understanding and parsing the set header and everything else that it includes. And so this is expensive. And then it's also if you think about it, kind of a wacky system, because you can do things like the following. So you can have at the very top of your own .cc file something like pound define, I don't know, some preprocessor defined macro that that redefines certain symbols, or maybe that switches on debug code or whatever. And then you have pound include set. And so what you do at the top before the pound include set might affect how the compiler reads the code that is included from set. So for example, you could do things like, pound define std my namespace. And everything that is in header files that references the symbol std, like namespace standard, is going to be read as if std had been replaced by my namespace. And so you can really shoot yourself in the foot there. Right. That's sort of the upshot of this. It's not just inefficient, but it's also unsafe to do it this way. It's not necessary that you yourself do this. You might be doing pound include some header file from some other project and then pound include set. And so what that other header file does will affect how the set header is read and understood. And so I think people understood fairly early on after 1967 that this is not a great system. And if you look at sort of the history of programming languages, you realize that every programming language that has been invented after C actually had a different system that made this more palatable. So I looked this up. There's a language that's called Modular by Nicholas Word, who also invented Pascal, that many of you perhaps have seen at some point. So that was in 1975, and there's a module system. Then Fortran 90, for example, has a module system. Java, Python, every language that you know of has a proper module system. And so modules replace sort of the textual inclusion of a pound include by a scheme whereby you have a file that describes what your project exports. And that is compiled into a machine-readable form where the compiler has stored what are the names of the symbols that are being exported. And then in your own project, instead of literal text inclusion of a header file, you say something like import, I don't know, std, or import, in my case, the library is called deal.II. Actually, we're talking about Kokkos. So you would want to do something like import Kokkos. And what that should do is it should import a number of declarations that Kokkos exports. And it should do this in a way so that whatever is being imported is always the same. It does not depend on what else you're importing. It does not depend on the state of your preprocessor, right? It should be a predictable thing where Kokkos can say, this is exactly what I'm exporting, and the namespace is called Kokkos, and it does not matter if somebody at the top of their own file had a pound define lowercase Kokkos, uppercase Kokkos, right? Renaming symbols. That sort of stuff should not affect what an import does. And like I say, every programming language since 1975 that has, respectable pedigree has such a system, except for C++. And I'm sort of a programming language aficionado. I enjoy reading about what people propose for C++, and there were proposals for a module system in the 2003 standard and the 2011 standard and the 14, 17, 20 standards. And these proposals never got traction. Some proposals were included and then removed from draft standards again, primarily because people couldn't quite agree on how exactly that's supposed to look like. And also, of course, it has to play with, I don't know, billions of lines of C++ that are out there. And it eventually took until 2020 or let's say 2018 for a proposal to be universally accepted, and then became part of the C++ 2020 standard, where you would have exactly the sort of system that I just described, right? Where you would have a file that describes what kind of symbols a library like Kokkos wants to export. And then the compiler would compile that file into some sort of machine-readable representation of what are the declarations that you want to export from Kokkos, so that in a user program, or maybe another downstream library, you would do something like import Kokkos, and it would import wholesale this machine-readable description of all of the declarations. And so this became part of the 2020 standard. And then let's just say it's not easy to implement. It's perhaps also not easy to use. And I think more than anything else, what makes this sort of awkward is you need to integrate this into build systems. So if you think about a system like CMake, for example, so CMake scans all of the source files that you want to compile and figures out transitively what are all of the header files that that this file is including. And that leads to compile dependencies, right? That if one of the header files changes, then the source file needs to be recompiled. If one of the header files is in fact generated by some other rule, then that has to happen before you can compile the .cc file. And so that same sort of infrastructure that already exists in CMake is something that first needed to be built. And for technical reasons, it is substantially more complicated for modules, because the names of modules that you're including or importing are not entirely obvious, and you can't easily get them by just looking at a file. You actually have to run a compiler for that. And so it's kind of awkward, and it took a few years before people have figured this out, how to build this into systems like CMake. How to build it into how to build the support for this into compilers. And I would say sort of in late 2024, compilers came along that can actually do this. And so I am one of the principal developers of a very large scientific software package. It's called deal.II, that incidentally also uses Kokkos. And I thought, because I like programming languages, I give it a try. I played with a small toy project that I have, a small library that has, I don't know, maybe 10,000 lines of code, and it turned out to be not all that difficult to make it work. Where I would just convert my header files into something that is a module description, where I converted all of my tests into ones that, instead of #include, did import the name of that toy project. And so that took, I did this over the Thanksgiving break. So our university is always closed for the week of Thanksgiving. And I think I spent Monday and Tuesday on it. And by Tuesday evening, I had something that actually worked reasonably well. And it could compile my test suite in about 50% of the time that it was before. And so that's, of course, one of the two benefits, right? So one of the benefits for modules is that it is more predictable, that you cannot, that the declarations that are being exported is decided by the exporting project and not the state of the preprocessor. And the other one was that presumably it is much faster to import, read a set of declarations that previously had been put into a machine-readable file than to #include tens of thousands of lines and parse them, right? And so the fact that it was 50% faster sort of validated that assumption. I'm going to come back to that later on. And so when that worked, I thought, well, it was sort of a nice experience. Let's give this a try with deal.II, which is a library that has on the order of maybe 900,000 lines of code, on the order of 1,000 files. So it's a fairly sizable project, really. I thought maybe I can get this done in 2 to 3 weeks of real work. That was a little bit optimistic. I think in the end, I spent about 6 weeks doing it. 6 weeks of actual work spread over, I don't know, maybe 6 months. So maybe I spend a quarter of my time on it, a day a week. But in the end, it works. I can make deal.II compile as a module, so that as a downstream user in an application, you can do import deal.II as opposed to pound include any number of header files that previously you would have used. So that was an interesting experience, and so what I wanted to do is show you how does this look like in practice. Before I go there, could I perhaps ask you to say how well you actually know the syntax of modules? Is that something that people are familiar with? So actually, there needs to be a concrete action point when you ask questions on Zoom. So if you do think that you know the module syntax, at least cursorily, raise your hand in Zoom. Okay, so if you have never heard of it or have no idea about it, raise your hand now. Okay, so that seems to be the majority. So in that case, let me show you how this looks like. Let me share my screen here. Sure, that's good. Okay, so you should be able to see a PDF of this paper right now, right? Okay.
Yeah, perfect.
So this is the preprint that I wrote about sort of my experience doing all of this. You can find it in archive. It's submitted to the ACM transactions on mathematical software, which I think is sort of the right place for this. So what I'm going to do is I'm going to show you real quick. This is what I should have put into a presentation and didn't. How do modules actually look like? At its core, the equivalent of what a header file is would be something like this here, where you say module at the top. So the module semicolon really just tells the compiler, hey, we're working in a module system and not in a header file system, okay? And then you're going to say export module linear algebra, for example, and forget about the rest here for a moment. So for you, this could be something like export module Kokkos.
Excuse me, Wolfgang. We have a request in the chat if you can increase the size of the text.
I bet I can. Maybe. Okay, is that better?
Yep.
Okay. Yeah, so you're saying export module, the name of the project, and forget about that colon here for a moment. And then you're going to say, well, what is it that I'm actually exporting? So in this case, this would be class matrix, or whatever it is in your project. And there could, of course, be other code and other declarations, but as long as you don't put export in front of it, it is not being exported. So you have control over what it is that is being exported, and everything that you can import are exactly the sort of things that are being exported. And in practice, if you convert existing projects, of course, there is going to be quite a lot of symbols, and instead of annotating each individual ones, you can say export curly brace open all of that code, curly brace close. So in projects like Kokkos, for example, or deal.II, where you have tens of thousands or hundreds of thousands of existing lines, you would conceptually convert a header file basically by putting module at the top, saying export module Kokkos, export curly brace open, and then the entire content of your header file, for example, curly brace close. So everything that's currently exported in the header file is being exported into the module. And perhaps that's something that later on you want to revisit. Maybe there are some internal functions that you need in the header file, but that you don't want to export, and then you can sort of selectively take them out of the export block. But that's sort of the idea. So then people realized that a project like Kokkos, for example, would have currently tens of thousands or hundreds of thousands of lines of header files. And they all need to export something. And so if you follow the scheme that I just laid out, that would mean that you have to throw all of the declarations into a single file where you're going to export stuff. And that's hard to do if you want to convert an existing project. And so what they invented is something that is called partitions. So this is this part here, where after the name of the module that you're exporting, you're saying colon and then the name of a partition. And so the way you should think about it is that every header file will be converted into one partition of the module. And so you can have many partition files that all export something. And what the module consists of is then the union of what all of these partitions export. So that's what you would do with header files. And then there are, of course, also things where you, I should say, so you can make partitions depend on other partitions. So for here in this partition, I export a class matrix. If I had another current header file that implements a matrix product, for example, then you would have another partition that is called partition matrix product. And the first thing it does is it imports the partition that declares the matrix, and then it exports its own matrix product, right? So that's sort of how this is supposed to work. And there's various other parts to it, but the only other part that perhaps is really of interest to us is at some point you have to implement the functions that you export from the module, right? And you have a different kind of module file that is called an implementation unit as opposed to an interface unit. And so in the implementation unit, you have the implementation of that function, right? So in the file that I showed you above, I only said export void matrix product semicolon. So I exported the declaration. Whereas here, I actually have the implementation of that function. I don't want to export the implementation, right? Unless this is a template or unless this is an inline function, the implementation should be something that is confined to my own library that can be compiled once. The people who import my library don't actually have to know anything about it. And so I have a file that does not export anything. And I also only say module linear algebra as opposed to export module linear algebra. So when I just say module linear algebra, it's an implementation file, whereas the file that I had up there, this one here, it said export module, that's an interface file. So the public interface of a module is defined by these sort of interface units, these interface files that have export module, whereas the implementations are defined by these non-export implementation units. So that's sort of the syntax. And I mean, we can probably argue whether this is, nice and good. And as somebody who enjoys programming languages, I have my thoughts about this. For example, that module is a keyword. Well, actually, it's not. You can name your variables like that, except module is a keyword only if it appears at the very beginning of a file and at the very beginning of a line of code. I don't know. That's not my favorite, right? I'm like, if you make it a keyword, make it a keyword. But things like this. I think at the end of the day, we can quibble about syntax, but you get the idea of how this is supposed to work, right? That there are files that describe the interface that is being exported, and there are files that describe the implementation, and typically you would compile those into, let's say, a shared library or an executable, for example, but the implementation is not part of the interface that you can import. And so what I spent these 6 weeks of work on is fundamentally that I was looking at deal.II, and I'm seeing 1,000 files that contain the sources. And when you have 1,000 files, there is absolutely no way that you can edit each individually, right? So I approached this from a really pragmatic perspective that if I were to get anywhere with this in an acceptable amount of time, then I needed to come up with ways how I can write scripts that convert the existing header files into interface files, and the existing .cc files, the implementation files, into implementation units. And so that was, I would say, half of the work, to come up with scripts that do this, because that allows me to convert all 1,000 files at once. So I have to write my script only once, but I don't have to touch 1,000 files. And the other part of it is that what I needed to achieve is that I can't just make edits to these files, because they need to continue to work in the header-based system, right? I mean, we've got hundreds or maybe thousands of users of deal.II, just like you have thousands or tens of thousands of users of Kokkos. You can't just replace the existing header-based system by a module-based system. You need to be able to provide both. And so the scripts are sort of my way of achieving this. And then what you find, and I mean, that's perhaps something that I don't need to go into great detail because I listed all in the paper, is that there are a million small cases that are allowed in header files, but not allowed in module files. So for example, you could have a static function that is defined in a header file, but you can't have a static function that you export as part of a module. And the reasons are technical and maybe not important, but what you find if you sit on the nearly a million lines of code is that, sure enough, there are plenty of header files where somebody has, for good or bad reasons, declared a static function. And so after writing these scripts, the majority of the time actually was spent in sort of, addressing one problem after the other that you find. And I wrote on the order of 150 pull requests for deal.II that sort of, address one problem after the other until I finally got to a point where I can compile the entire library. And so what I want to show you for the next few minutes is how does it actually work, right? And so I looked at some numbers that I get them. So let me just scroll down to the results section of this paper. The paper got long, as you see. So what I was mostly interested in is, does it compile faster, right? So the promise of modules was that with modules, you would be able to compile the equivalent of the header files once, and then you get sort of a machine readable file that contains all of the declarations. Whereas so far, every time you include a header file in a source file, the contents of these header files have to be compiled from scratch. And so here's a table that shows compile times for deal.II. And so we compile deal.II twice in debug and in release mode. So what you see is that so the traditional build versus module build in terms of CPU time, for example, drops from 60 to 50 minutes. And the library size stays roughly the same, which is to be expected because, of course, every implemented function in deal.II that exists in the traditional system must also exist in the module system. So let's say CPU time reduced by 1/6, so 15%. Okay, it's not a huge difference, but it's nice, right? And the same thing in release build from 47 to 37. Okay, so in that case, it's a difference of maybe 20 or 25%. You see roughly the same. So deal.II can build with, on the order of 30 different external dependencies. So we rely on Kokkos, but we also we don't have to build with Trilinos and with PETSI and with UMFPAC and with a whole bunch of other libraries. And so when you include all of these, it takes a lot longer to compile, but you still see the same sort of benefit, both in debug and in release mode. So this is for compiling deal.II itself. And I think, that's nice, right? I would say that a 10-minute difference in compile time is not, huge, but it makes a difference. And I think if you think about, sort of, I don't know, environmental concerns or sort of the issue of running every patch that we submit through a whole bunch of regression testers, a reduction by 15 or 20% matters, right? I think that's worthwhile. So this is for the library itself. And then I converted all of the tutorial programs. So deal.II has on the order of 100 tutorial programs. And of course, right now at the very top, they all have a dozen, pound include deal.II this, pound include deal.II that. So replaced all of these includes by a single statement import deal.II, which imports the machine readable union of what all of these interface units or interface partitions have exported. And I was hoping that that compiles substantially faster too. And so for each one of these 100 tutorial programs, let's say for those that I could get to run, the other ones has nothing to do with modules. There are some technical reasons why I couldn't build the other ones. So the build time for the header-based system for each one of these tutorial programs is this blue bar. And the build time for these orange ones is the orange bar. And you can see that for about 2/3 or maybe 3/4, compile time really is shorter. But then there's a bunch of files for which compile time actually has gotten much longer, between 2 and 4 times longer. If you do import deal.II as opposed to pound include this and that. And to be honest, I don't know what the reason is. I suspect that maybe compilers are not yet very efficient at this. This is the very first version of Clang that could successfully compile modules. And so I wouldn't be greatly surprised if we end up with a substantial improvement over the next couple of years. But so this is the outcome of this, right? So I think at least for downstream projects, the way you should see this experiment is it's not entirely obvious whether it's successful. I think there's promise there, but it remains to be seen whether this actually goes anywhere. But for compiling the library itself, 15 or 20% improvement in compile time is noticeable. So that's sort of what I had to say. And perhaps then we have 20 minutes where we can have a chat about what is it that you want to know about this, or what your thoughts are.
Thank you very much. So indeed, we have time for a few questions or for some discussion. Are there any questions in the chat or in the audience? Yeah, Christian, Vasily.
Can I just go?
Yeah.
Yeah, so I read your paper a while back, and the one thing I wondered about, although from your description now, maybe I misunderstood, but so your experience seems to be on one level a bit opposite of what I would expect, because I would usually expect that the build time for the library that you modularized might not necessarily increase a lot, but you would expect to see the big increase from the examples that are just importing that, rather than including it. And I got the impression from one part of your paper that you maybe had modularized the examples as well. So not just changing their includes to imports, but also changing their internal files to be modules. And that could obviously have a kind of affect the output. So sorry, the outcome of the timings. And but from your description here, it doesn't sound like you did that. So I'm not sure if I misunderstood it.
So the tutorial programs are all individual files, just like self-contained.
Okay.
And so for those, there is really no difference between the modular or non-modular version, right?
Okay.
It's really just, do you have some includes, pound includes at the top, or do you have an import at the top? In the paper, I show results for another project that's called Aspect. It's a large application.
I think that's the one I was thinking of. Yeah.
And that one I also modularized, and I didn't show the results for that. Let me show that real quick. Yeah. So for that one, the module build time went from 25 to 38, and you're exactly right. That's counterintuitive. You would expect the compile time to go down. And yeah, that falls in the category of, I don't know. I wished I could tell you.
To me, it's even more surprising if you're talking about these tutorials just being a single file, and if you switch them from include to import, and then you're just timing the build time of that file and not the dependent library. That's the one case that I would really expect for modules to be an obvious improvement.
Correct. Yes, I totally agree. You would expect the time to go down, but like I said, there's some files for which compile time is between 2 and 4 times larger.
Yeah.
For most of them, it's like 20% smaller. Right.
Have you by any chance tried this again on a more recent version of Clang? Because I'd let you say it definitely has changed a bit in recent.
Yeah, so the version that I used is 20.1.7, I think. So that was the latest version on the 20 release branch that from May, I want to say. And it is conceivable that in Clang 21, there's a difference, right? But it's a few months of development. Who knows? Clang 21 came out, I don't know, 2 or 3 weeks ago. I haven't tried it since then. But it's on my list of things, of course, to do.
Yeah, there's one flag that I haven't actually. I'm using Clang 20 as well, and I haven't tried 21 yet. But there is one flag that is available. I'm not sure if they switched it on by default in the more recent Clangs, but on 20 you can turn it on. I think it's called.
It's reduced BMI, right?
Okay, you know about it.
Yeah,
because that can make a huge difference in some cases.
Yeah, so that led to internal compiler errors in version 20, and Out of these 6 weeks, I probably spent 4 days trying to work on small test cases that I could give to the guy who develops the module part and claim it. So I think that will be fixed or is fixed.
Okay,
Yeah.
thank you.
I mean, like I say, this is the first version of compilers, and we would expect that there are problems, right? That does not greatly surprise. I tried it with GCC, for example, and GCC so all of this, of course, is highly technical, right? And GCC has a different interpretation of one of the rules in the standard, and that leads to hundreds of errors in common header files, and so I just couldn't make it work. I
think I know which rule you're talking about, and if so, Clang has started to implement the same rule as well, so it's gonna.
Yeah. So
We
I
we
think
have a question in the chat. Can you just repeat the name of the flag you were talking about earlier? The BMI.
I think it is called -f reduced BMI or something like this. I forgot the and maybe there are modules reduce BMI. Okay, yes, and Cameron. Yeah, so there's room for improvement in compilers, and that does not surprise.
Thank you. So maybe I will just announce that our next Kokkos Tea time will happen on the 15th of October. Same place, same link, same time. And we can continue the discussion, but since the official duration is 45 minutes, we now have time for open discussion. Yeah, and I think Damien has had his hand raised, and then we can move to the question of Philip in the chat.
Hi, Wolfgang. I was wondering whether you ever had done the experiment on deal.II in the past using other techniques such as precompiled header or Unity build or stuff like that to speed up the build.
We have, and in particular, we've done it for this code aspect for that big application for which I showed you the last table there, where this is actually automatically enabled by CMake. So CMake allows you to say switch on precompiled headers automatically, and so that works. I don't have numbers though. Yeah, so I can't. I don't have detailed experience in it, and I certainly don't have numbers for this. The Clang folks built the module system based on their precompiled headers infrastructure. So you would expect that there is not a huge performance difference.
Yeah, that's exactly what I expected, that you would have, if you had managed to do it in the past, you would have roughly the same gains. The Unity build though sometimes can be surprisingly good, but it's it depends on what notifying you do in your library. I had tried with Kokkos Tea, and we do a lot of things we shouldn't do with macros that don't play well with Unity builds.
We have that same issue. Yeah, we built deal.II through Unity build. So if you're not, for the rest of you, if you're not familiar with this, Unity builds basically say, throw all of the .cc files into one and compile that at once. Maybe if that's too big, then throw all of your 1,000 files into 50.cc files and compile only those 50. And that should be more efficient because now you only have to do 50 times the processing of all of the standard library as opposed to 1,000 times. and it is more efficient. So I think that's a clever system. The only problem, of course, just like Damien just said, is that if you have a pound define of some macro in one .cc file, if you copy paste a whole bunch of .cc files together, then suddenly the definition of that macro leaks into everything else that comes after that file in the combined in the Unity .cc file. Yeah, you can. So, you know, to be honest, I didn't see this as sort of a project of figuring out whether modules are so much better. I wanted a hobby project. I enjoy these sort of things, and so I really I wanted to figure out, does it work, right? Not does it necessarily work better than Unity files or precompiled headers. I think if you think about, 10, 20 years in the future, right? I think it's very clear that modules are going to be what people who write C++ code use and want to use, right? I think it is from a language perspective, a superior system to includes, because it separates the concerns, right? It allows you to say what you want to export, and it is not so brittle with preprocessor defines. And so I think as an ecosystem of scientific codes, we have to move there, whether we want to or not, because the students will expect it, and because the downstream projects will expect it. And so my interest was, well, let's see what it takes to make it work, right? So I didn't think of this as in competition to precompiled headers or Unity builds, but as like, well, what does it take to actually make it work? Because we, at some point or other, will have to do it anyway.
Yep. Yeah.
I assume before you went into doing your transformation, you put good thoughts on how going forward you're gonna maintain this, and how whether this is acceptable, the mess it makes in your source code. Can you share a bit of your thought? I mean, because the other alternative would have been putting a bunch of export everywhere, which is also a very hard enterprise. Can you share a bit about your thoughts and how you chose your strategy?
Yeah, so I mean, all of the patches that I wrote have been merged. I think there's one CMake thing that I'm still thinking about, but all of the things that were necessary, including the conversion scripts, are in the code base and are in fact in the latest release 9.7. And we have a CI step that builds modules. So this cannot break. You're exactly right. I mean, the experience is that whatever isn't tested doesn't work, right? And but this is tested. We do build modules for every pull request as part of the CI check, and if you break something, then that's going to show up, and the patch will not be merged. So you cannot use anonymous header spaces, anonymous namespaces, or static functions in header files anymore, because the compiler would flag it. You can't introduce cyclic dependencies between header files anymore, because the CI would flag it.
Thank you. I would have a million other questions, but I guess I'll try to grab you at a conference or something.
Yeah, and I mean, also, if this is something that you're interested in, we can always, I've known Damien for how long? 15 years now, since you were a student in at A&M. So
Wolfgang is my co-advisor on my PhD, for those who don't know.
Yeah. So send me an email and we'll put something on our calendars to have a Zoom call.
Yeah, Daniel Arndt has been doing some exploration on our side as well, and
yeah,
he's moved very, very fast. But I am still hesitant on a few things, because I want to see how we can maintain it, and whether we just save time now and we're gonna regret it later. Anyway, thank you so much about your talk. It was very interesting.
Yep.
Yeah, I think we also have a question in the chat. Philippe, do you want to ask it directly?
Yes, I actually can. So, because you just briefly mentioned templates, so like how does this translate to a code where the library itself is already heavily templated? The second question then, like beyond compile time improvements, are there any like long-term advantages from like beyond the ecosystem? Like assuming the ecosystem develops well, what else do we get?
Yeah, so let's do the templates first. I mean, the system works fundamentally like you do templates right now, right? If you have a template in a header file, where you also provide the implementation, then you just export the template and its implementation from an interface file, and it is so. I should have been careful to say that what you can export is not just declarations, but it is also implementations, right? You would just say export template something or export curly brace, and then everything that you currently have in a header file you can export. So that is not a problem, and you can also use the same scheme as currently, where you just export the declaration. You put the implementation into a .cc file, as long as you provide explicit instantiations of that template. So that continues to work. I would say that 80% of all entities in deal.II are templated, and that works just fine. So long term, I mean, I think the way you should really think about this is that the world will use modules whether we want it or not. I mean, companies like Facebook and Google and all of the others that build huge code bases are using this in production today. They have the advantage that they control compiler versions, and they control the entire code base. And so, Google, for example, has a monorepo where every piece of code that is written in Google sits in one repository. Most big companies actually use that sort of scheme. And so every time a piece of Google code is compiled, it is compiled with the same compiler that is under control of the engineering team. And so they can say, we're switching to client 21. And that means that for everything they do from here on out, they can use modules, and they do. And so I think one of the things that worries me a little bit is that industry moves to modules, and we will have to teach our students modules because that's what they will use in their jobs. But the academic system does not have the bandwidth to convert the codes, and we're going to be stuck with the equivalent of Fortran 77 code in 2040, except that it's header-based C++, right? So I think it would be very nice if we, don't end up in that situation. I do hope that, in a few years, all of the major projects do offer modules, right? And if you absolutely need to, well, then maybe you can continue to work with the header-based system, but at least you can use modules.
Thank you.
I don't
Yeah, I
know
mean,
if
this
that's
is it's always good to hear this over and over again, especially given the amount of students that actually go to industry. It's always good to give them some additional incentive on like crossing that threshold.
Yeah.
Great. Thank you.
And I mean, there's also the issue, of course, that many of our projects are also used in industry, right? I mean, I can only imagine that there's, dozens or maybe hundreds of industry projects that use Kokkos, right? And if the industry folks use modules, then Kokkos will have to provide a module, and the same for deal.II.
Okay, I believe we have time for maybe one last question. So is there one last question? If not, I'm extremely happy because I still have a million questions. I don't see it.
Right. So I mean, I have another meeting in 2 minutes, but I would be happy to talk to anybody who's interested in this sort of stuff and share my experience.
Maybe to conclude, have you played with binary modules in Fortran? Because this is a mess. this just doesn't work. It is not compatible from one compiler to another. So for distribution, it's really a problem. It prevents parallel compilation because, well, the implementation generates the module, so anything that uses it has to be compiled later. So for distribution, it's really a problem in the Fortran world, and people end up writing C headers, and that's the actual interface. What does C++ do differently to have modules that actually work?
Yeah, so the truth is, it's not actually all that different. All of the Fortran folks are quite happy because Ninja can now finally compile Fortran modules, because that was the infrastructure that it needed to build for C++, for example. So it is true that the machine-readable module descriptions that you can import are compiler dependent. And that's an issue, and I spent a lot of time in the paper to really think about this. What does that mean? And I think in practice, what that means is that you cannot distribute the machine-readable module file because it's compiler dependent, compiler version dependent. And what you will have to do is that Kokkos just distributes its own interface units, the interface partitions, and every downstream project with the compiler that they use will have to recompile the module description, and that takes time. So I quantify that in the paper. There's going to be, every time you start a new project, it has to recompile the upstream files module first. Is that great? No, I wished I had come up with a different system, but that's how it is.
Okay, in any case, thank you very much for this great presentation, explanation, discussion. And I believe, yes, there is a lot more to discuss, but maybe we can have this discussion in another place on Slack or whatnot. So see you everyone in 1 month from now on the 15th of October. And thank you again, Wolfgang. Bye-bye.
My pleasure. Okay, see you.